Okay, that's it for part one. That's the history of opioids. Now we'll transition and study some of the neurophysiology and the function of opioids in the brain. We'll look at the four major types of opioid receptors and the endogenous opioids, as well as how they change neural function. There are at least four different types of endogenous opioids in the central and peripheral nervous systems. All these receptors rely on a metabotropic G protein mechanism, so we can expect them to be slow. And the effect they have on neural activity is to hyperpolarize the cell, so they become less likely to fire, and neural activity is inhibited. The endogenous opioids are constructed in the cell nucleus from large precursor peptides, and those molecules are then transported along microtubules in vesicles down to the synapse, where they are converted into opioids. Opioid receptors are distributed differentially throughout the brain. In particular, the highest density areas include the nucleus accumbens, the ventral tegmental area, and the periaqueductal gray. And this distribution can help explain things like the addictive potential of opioids, as well as their analgesic effects. We'll look further on into the neural circuitry underlying pain perception to try to explain these effects. So as I mentioned, opioids hyperpolarize neurons and result in a lower firing rate. So let's take a minute to look at the mechanisms that underlie that effect. There are at least three different mechanisms by which opioids can reduce neural activity. There's postsynaptic inhibition, axoaxonic inhibition, and presynaptic autoreceptors. On the right-hand side, you can see three different panels illustrating these different effects. Starting from panel A, we'll look at postsynaptic inhibition. The idea here is that the opioid neuron opens calcium channels on the postsynaptic neuron, resulting in an increasingly hyperpolarized cell. As the interior of the cell becomes more negative, it becomes less likely to fire, and the neuron is inhibited. In the second panel, we can see axoaxonic inhibition. And here, the opioid neuron synapses on the presynaptic neuron, closing calcium channels and preventing the cascade, leading to action potential in the postsynaptic neuron. Finally, there's the presynaptic autoreceptors. And this is like a negative feedback loop, so that when the concentration of the opioid becomes large, the autoreceptor will downregulate the amount of neurotransmitter being released. So let's take a bit closer look at postsynaptic inhibition. All these actions are going to be activated by a G protein receptor. And in this case, we're opening the calcium ion channels. Remember back early on in the course where we talked about the resting membrane potential based on the concentration and charge of different ion species inside or outside the cell. Remember that potassium has a much larger concentration inside the cell at the resting state. So if we open the potassium channels, there will be an outflux of potassium ions leaving the cell. And as the more positive charges leave the cell, that leaves the interior more negative than it would have otherwise been, and thus hyperpolarizing the neuron, making it less likely to fire. Axoaxonic inhibition acts on the presynaptic neuron voltage-gated calcium ion channels to reduce their release. Now remember, calcium is very important for neurotransmission and initiating action potentials. Without the calcium, due to the inhibition, the postsynaptic neuron will be less likely to fire. So finally, we'll talk about opioid autoreceptors. The autoreceptors live on the presynaptic neuron, and their action is to reduce the amount of intracellular calcium. If calcium can't be released, then it can't initiate an action potential in the postsynaptic neuron. So remember, all of these receptors use the metabotropic G protein mechanism, which relies on second messengers like cyclic AMP. By reducing the amount of those second messengers, we can reduce the amount of intracellular calcium in the presynaptic neuron, resulting in decreased excitability. And you might remember from previous lectures, this is just like the dopamine D2 receptors.